Example 2a was pretty long and didn't leave us much space for example 2b, but I believe that 2b, or not 2b, will not take up too much space. It should be a little bit more straightforward, I believe. So we're going to start off with the ratio test, as always. Ratio test is going to tell us to take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, which is the limit as n approaches infinity of x over 3 raised to the n plus 1 divided by x over 3, or times 3 over x raised to the n. We'll take the absolute value of that, and that's going to work out to cancel out almost everything. We're going to get the limit as n approaches infinity. We have 1x left over on the top, and we have 3 left over on the bottom, and that has to be less than 1 for the ratio test to conclude that the series converges. So if we have x over 3 has to be between -1 and +1, that means that x has to be between -3 and +3. All right, so our interval of convergence is going to go from -3 to +3. The only question now is what do we do about those endpoints? The center here is 0. The radius of convergence is 3. Radius equals 3. They didn't ask for the radius, but I like to include that anyway. So then we ask, what about x equals the endpoints? X equals -3. We take the sum as x equals -3. I'm just going to replace the x with -3, and that's going to be the sum of -1 to the n. So that's going to be 1 plus -1 plus 1 plus -1 plus 1 plus -1, and that diverges by oscillation. Diverges by oscillation. Or you can do the nth term test to show that as well, because the terms don't approach 0. Then we have to check the other endpoint. The other endpoint, x equals 3. When we try to plug in x equals 3 here, we get 3 over 3 raised to the n, or 1. 1 raised to the n is just the same thing as 1. That also diverges by heading off to infinity. So both of these use the nth term test to show the divergence. So that means that we do not include the endpoints, do not include -3, and do not include +3, because 3 and -3 cause this thing to converge. And if you recognize this series, we just proved, using the ratio test, what we already knew about geometric series, right? So we actually not only know the interval of convergence here. The interval of convergence is -3 to +3, not including the endpoints. But we also know what this converges to if we think about the geometric series convergence formula. More on that later. All right. So on to 2c. Again, they're giving us the series here. We don't have to generate it, so we just jump straight into the ratio test. So the ratio test tells us to take, I keep on saying the ratio test tells us to take the limit as n approaches infinity of the absolute value of, again, we don't have to worry about the oscillating part of this. We just do excuse me, we do the positive value of this. And anywhere where we see an n, we replace it with n plus 1. Notice the parentheses there, that's important. So anywhere where we see an n, we replace it with n plus 1. All right. So that's going to be a sub n plus 1. Now we're going to do a sub n. We're going to divide by a sub n, so that means multiplying by the reciprocal. So the 2n plus 1 factorial goes on the top, and the x to the 2n plus 1 goes on the bottom. Now you might want to distribute to figure out what that first fraction actually looks like. We've got 2n plus 2 plus 1, so that's 2n plus 3 on the top, and also 2n plus 3 on the bottom for the exponent and the factorial, respectively. And here we've got the same old, same old. And as we like to see in the ratio test, exponents and factorials cancel out. So we've got 2 more x's on the top than we do on the bottom. And we've got a 2n plus 3, and we've got a 2n plus 2 on the bottom. The 2n plus 1, the 2n, and the 2n minus 1, and all of those other ones cancel out with the 2n plus 1 factorial in the numerator of the other fraction. So we've got absolute value bars here, and we want to ask the question, what happens here as n gets really, really big? Well, let's again think about this as we did with that first example, 2a. We can factor out the x squared and just ask what happens with all the n stuff. And we should recognize that we've got a growing denominator here and a constant numerator. So whatever value of x I pick, no matter how big that x value is, this is eventually going to go to 0. And 0 is always less than 1. Therefore, the interval of convergence is all real numbers. Okay, so this thing converges to something. We don't know what it converges to, but it does converge to something for all real numbers. All right, and as we look at this 2D example, you might already know what's going to happen here. You might notice that both of those things are growing crazy fast, but we'll go ahead and do it anyway. The ratio test is going to tell us to take the limit as n approaches infinity of the ratio of a sub n plus 1, which is n plus 1 factorial times x minus 3 raised to the n plus 1, over a sub n, which is n factorial times x minus 3 raised to the n. And that thing reduces. We end up with n plus 1 on the top, and we actually end up with an x minus 3 on the top as well, and just a 1 on the bottom. So if you want to factor out the x minus 3, sure, have fun. And then we just ask what happens, no matter what we pick for x, what happens to the limit as n approaches infinity of n plus 1? Well, this thing is equal to infinity. So the only time we're going to get any sort of convergence is when x equals 3. So x equals 3 is the center of the power series. So the interval of convergence is not even an interval, it's just x equals 3. So that would be your scenario 1 situation. Not a very exciting result, but sometimes that happens. The radius equals 0 for that example that we just did. And we would say that the series converges only at c. Okay, so there is no interval of convergence. It's just a single point.